Welcome everyone to Algebra 2, Section 4.8, solving quadratics by the quadratic formula and using the discriminant. So the quadratic formula, first of all, is x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. And the a, b, and c from this formula come from our standard form of quadratic. We'll see if it loads here, where it's ax squared plus bx plus c. So we first need to write our equation in standard form with everything equal to 0, so that way we can identify a, b, and c correctly, and then you substitute them into the formula and simplify. You just follow the order of operations. Now this formula works for every single type of quadratic that you'll ever encounter. Has a 100% success rate. However, it does end up taking quite a bit more time and steps than some of the other methods, oftentimes. So on number 1, we make sure that it's all in the correct form. Ax squared plus bx plus c equals 0. It is in fact in that form. And so we identify a as 1, b as 2, c as negative 63. And I won't be writing that out every time, but I am writing it for this initial one. And as we plug this one in, remembering that the formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a, it'll look like this. X equals negative of 2 plus or minus the square root of 2 squared minus 4 times 1 times negative 63 all over 2 times 1. So you just plug in a for a, or 1 for a, 2 for b, and negative 63 for c. Now we work through our order of operations. So negative of 2 is negative 2 plus or minus the square root. 2 squared is 4. Negative 4 times 1 times negative 63 would end up being 252. And we're adding those together. Positive 52 over 2 times 1, which is 2. Then we're going to look to combine the 4 and 252. So we get negative 2 plus or minus the square root of 256 over 2. And a lot of times people will end up just jumping from this step to this step, especially if they end up typing what is in here into a calculator. And we can now do the square root of 256. If we can do the square root, we do. If not, we look to simplify this square root as much as possible. But the square root of 256 is 16. And so we make our two cases just like we did back when we did factoring and square rooting, or not factoring, excuse me, but square rooting and completing the square. We're going to have x equals negative 2 minus 16 over 2, and the other case, x equals negative 2 plus 16 over 2, and it really doesn't matter which one you put on either side necessarily. But in this one, we have negative 2 plus 16, which is 14. And if we take 14 divided by 2, we end up getting x equals 7. And in the other one, we end up getting negative 18 over 2, which is negative 9. So our two answers are x equals negative 9 and 7 from least to greatest, or you could also just write 7 and negative 9, or two separate boxes, or however you'd like to do that. Number 2 here, this is in the correct order. A is 6, B is negative 11, C is negative 10, so plugging this in would be x equals negative of negative 11 plus or minus the square root of negative 11 quantity squared minus 4 times 6 times negative 10 all over 2 times 6. As we work through this math, negative of negative 11 is positive 11 plus or minus the square root of 121 plus 240 all over 12. Combine the 121 and 240, and we end up getting plus or minus the square root of 361 all over 12. And this ends up being 11 plus or minus 19. Square root of 361 is 19 all over 12. I'm going to go ahead and make my two cases here. And I'm kind of running out of room, so I'm going to go off to the side, where I have x equals 11 plus 19 over 2, and x equals 11 minus 19 all over 2. So this first case here ends up getting me 30 over 2. Second one is negative 8 over 2. And so this top one is x equals 15. Whereas the bottom one here is x equals negative 4. Hope I did something wrong here. Oh, silly me, silly me, silly me. My apologies, everybody, on this. Let me undo much of what I just did. I put 2 in the denominator here, but it is not 2 in the denominator there. It is 12 in the denominator over here. Gosh darn it. That's better. So I get 30 over 12 and negative 8 over 12. And now this top one reduces by 6 to become 5 over 2, or 5 halves, whereas the bottom one reduces by 4 to become negative 2/3. That looks a little more accurate. Let's look at number 3 here. Number 3, we notice it's actually not in the correct order. So we're going to have to do the negative x squared plus 2x minus 1, subtract 1 to get everything equal to 0. And then we plug this into our quadratic formula, which is x equals negative of 2 plus or minus the square root of 2 squared minus 4 times negative 1 times negative 1 all over 2 times negative 1. So that's negative 2 plus or minus the square root of 4 minus 4 all over negative 2. That's negative 2 plus or minus the square root of 0 all over negative 2. And last I checked, the square root of 0 is just 0. So you get negative 2 over negative 2. Don't have to worry about a plus or minus this time. Now there's only going to be one solution, and that one solution is x equals 1. Moving on to number 4. Once again, it's not equal to 0, so we need to subtract 4x and add 15. Or if you wanted to, you could add 2x squared and subtract 3x. Either way would accomplish the same task. Let's just say I move things from the right to the left. So I get negative 2x squared minus 1x plus 15 equals 0. So I plug this into my quadratic formula, and I get x equals negative of negative 1. Yes, 2 negatives there, 1 from the b and 1 from the formula. And the 1 from the b goes inside the parentheses, the 1 from the formula goes outside the parentheses. Plus or minus the square root of negative 1 quantity squared. Once again, inside the parentheses is a negative 1. Plus or minus, excuse me, not plus or minus, but rather just minus 4 times negative 2 times 15. All over 2 times negative 2. X equals 1 plus or minus the square root of 1 plus 120 all over negative 4. So that's 1 plus or minus the square root of 121 all over negative 4. And the square root of 121 is 11, so 1 plus or minus 11 all over negative 4. So I'm going to go ahead and make my two cases here, where you get x equals 1 plus 11 all over negative 4, and x equals positive 1 minus 11 all over negative 4. So the left one here ends up being 12 over negative 4, whereas the other one ends up being negative 10 over negative 4. And this left one ends up giving me negative 3, whereas the right one gives me positive 5 over 2. And those are my two answers. Moving on to number 5. We have to add or subtract 24 from each side, and we get 9x squared minus 25 equals 0. So as I go through and plug things in, I notice that my b is lacking. I don't have a bx term, and that means my b is 0. So it's negative of 0 plus or minus the square root of 0 squared minus 4 times 9 times negative 25 all over 2a, or 2 times 9. Negative of 0 is just 0, and I don't have to write 0 plus or minus. I can just write the plus or minus. I still do need the positive negative though, because I am making sure that I'm including both cases. 0 squared is 0, so I'll just write the negative 4 times 9 times negative 25 as 900. All over 18. And positive negative square root of 900 is positive and negative 30. All over 18. And I don't really have to split my cases here, because whether it's a positive 30 or a negative 30, and if I reduce that in 18, they reduce to the same number. So I just get positive and negative 5 over 3. Number 6 here, I subtract 10x from each side, and I get 8x squared minus 10x equals 0. So here my c is 0, because I'm missing a number that's just by itself, a constant. So as I plug things in, I get x equals negative of negative 10, plus or minus the square root of negative 10 squared, minus 4 times 8 times 0, all over 2 times 8. So that's positive 10 plus or minus the square root of 100 minus 0, or just 100, all over 16. And noting that the square root of 100 is 10, we get x equals 10 plus or minus 10, all over 16. I'll go and split this into my two equations, getting x equals 10 plus 10 over 16, and x equals 10 minus 10, all over 16. 10 plus 10 is 20 divided by 16, and 10 minus 10 is 0 divided by 16. And 20 divided by 10 is 2. Sorry, I'll try that again. 20 divided by 16, I need to be clear with my 16 here. 20 divided by 16 reduces by 4 to become 5 over 4. And 0 divided by 16 is just 0. And those are my two answers. Moving on to the next page. We're going to subtract 4x and get x squared minus 4x minus 9 equals 0. Plug this into my quadratic formula, and I get x equals negative of negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times negative 9, all over 2 times 1, or 2a. So this is positive 4 plus or minus the square root of 16 plus 36, all over 2. And that is 4 plus or minus the square root of 52, all over 2. The square root of 52 reduces, or simplifies I should say, into positive negative square root of 4 times square root of 13, or just positive negative 2 times the square root of 13, because the square root of 4 is 2. You can make that two separate steps from the blue to the red, where you add in the middle step where you call it square root, instead of square root of 52, you call it square root of 4 and square root of 13, multiplying. Next, we can't actually combine these, so there's no use separating them into positive and negative, but we can reduce by 2. And if 2 reduces in all of these into both here, we can reduce it into each. We can divide each of them by 2 and get 2 plus or minus 1, or just square root of 13. 1 square root of 13 is square root of 13, all over 1, or just that. Moving on to number 8. Going to subtract 8x and add 1 to get negative 2x squared minus 8x plus 18 equals 0. Plug this into my quadratic formula, and I get x equals negative of negative 8 plus or minus the square root of negative 8 squared minus 4 times negative 2 times 18, all over 2 times negative 2. And so that's 8 plus or minus the square root of 64 plus 144 all over negative 4. And so it's 8 plus or minus the square root of 208 all over negative 4. The square root of 208 is the square root of 16 times the square root of 13. Once again, the square root of 16 times the square root of 13, which I'm going to go ahead and call the square root of 4 times the square, or excuse me, normal 4 times the square root of 13. The square root of 16 is 4. Since 8 and 4 can both divide by negative 4, we can go ahead and reduce these as well without having to split it up into 8 over negative 4 and plus or minus 4 square root of 13 over negative 4, but you're more than welcome to go ahead and split that up. And I'm going to get negative 2 plus or minus, and here's the thing, I could write plus or minus a negative 1 square root of 13, but the thing is, if I do plus a negative square root of 13, it might as well just be minus square root of 13. And if I do minus a negative square root of 13, it might as well just be plus a square root of 13. So by saying plus or minus, and then having another negative there, it ends up being quite redundant, very unnecessary. And so if we just do negative 2 plus or minus square root of 13, we get the same cases as if we had the negative there. And so we go and remove the negative if we catch that. If you don't catch that and just leave the negative there, it's not necessarily wrong, it's just unnecessary. Moving on to number 9. Once again, pending at loading. We have negative 8x squared plus 7 equals 4. I subtract 4 from each side, and I get negative 8x squared plus 3 equals 0. Noticing I'm missing a b term, so my b is 0. X equals negative of 0, plus or minus the square root of 0 squared, minus 4 times negative 8 times 3, all over 2 times negative 8. So I get positive negative square root of 96 all over negative 16. And the square root of 96 is the square root of 16 times the square root of 6, which would be 4 times the square root of 6 all over negative 16. I can in fact reduce 4 negative 16 by 4, and so I get plus or minus square root of 6 over negative 4. Once again, the negative on the bottom is quite redundant, because if you take a positive divided by a negative, you get the negative, so you might as well just have this. And if you take a negative divided by a negative, you end up getting a positive, so you might as well just have the positive version. And so it ends up being quite redundant that you have a negative 4, and so you might as well just write 4. But once again, if you write the negative there, I'm not counting it wrong. Number 10 here. Negative x squared plus 10x equals 8. So I'm going to go and subtract 8 and get negative x squared plus 10x minus 8 equals 0. Plug this into my quadratic formula, and I get x to be, or x to equal negative 10, negative of 10, plus or minus the square root of 10 squared minus 4 times negative 1 times negative 8, all over 2a, or 2 times negative 1. So it's negative 10 plus or minus the square root of 100 minus 32 all over negative 2, which would be negative 10 plus or minus the square root of 68 all over negative 2. Square root of 68 is the same thing as the square root of 4 times the square root of 17, so I'm going to call it 2 square root of 17. And negative 10 and 2 reduced by negative 2. And once again, the negative here ends up being redundant with that plus or minus, but we still definitely need it. Take it into account with those. And so we get 5 plus or minus square root of 17. Moving on to number 11. It is equal to 0. How exciting. So we plug this in. X equals negative of 8 plus or minus the square root of 8 squared minus 4 times negative 3 times negative 7 all over 2 times negative 3. And so it's negative 8 plus or minus the square root of 64 plus minus 84 all over negative 6. And so that ends up being negative 8 plus or minus the square root of negative 20 all over negative 6. Notice a square root of a negative, so we're going to have imaginary solutions here. So I get negative 8 plus or minus 2i square root of 5, because square root of negative 20 is the square root of negative 1 times the square root of 4 times the square root of 5. Square root of negative 1 is I, square root of 4 is 2. And that's all over negative 6. I reduce by 2 on both here and here. Because I reduce everything by 2, no more, no less, I can go ahead and just keep it all together when I do it. And call this negative 8 divided by negative 6 positive 4 and a positive 3 plus or minus 1i, or just I, square root of 5, as 2 and 6 reduced by 2 become 1 and 3. And those are my two answers. On number 12, 5x squared plus 9 equals 4x plus 5. I subtract the 4x plus 5, and I get 5x squared minus 4x plus 4 equals 0. I plug this into my quadratic formula, and I get x to be equal to negative of negative 4 plus or minus the square root of negative 4 quantity squared minus 4 times 5 times 4 all over 2 times 5. And that is 4 plus or minus the square root of 16 minus 80 all over 10. And so that gives me 4 plus or minus the square root of negative 64 over 10. The square root of negative 64 is the square root of negative 1 times the square root of 64. So that's 4 plus or minus 8i over 10. I cannot combine 8i with 4, whether the 8i is positive or negative. And so I'm just going to go ahead and reduce 10 and 4 and 10 and 8 all reduced by 2. And so I'm going to reduce every single thing by 2 and get 2 plus or minus 4i all over 5. On to the next page. We're going to talk about this idea of the discriminant. The discriminant is just part of the quadratic formula. And the part of the quadratic formula it is the b squared minus 4ac. That's the part that's underneath the square root. And the discriminant here is a numerical value that tells what type of roots a quadratic has, as well as how many roots a quadratic has. So depending on the discriminant, we'll see that. And if we look back and see what was underneath the square root to determine this each time. And actually, I'll go back and showcase that in a moment after we look at these. So if d, or the discriminant, is greater than 0, we're going to have 2 roots. Now, if it is a perfect square, specifically, we're going to have 2 rational roots. Rational means it can be expressed as a fraction, or also sometimes it's an integer. And if it's not a perfect square, but still greater than 0, we're going to have 2 irrational roots. And let's showcase what problems like that we had that on. So, number 1, for example. It doesn't want to show my rating on here, I suppose. There we go. The discriminant, or what we got underneath the square root, was 256. That is a perfect square that was greater than 0. And so we ended up having 2 rational answers, negative 9 and 7. We saw the same thing here on number 2, where our discriminant was 361, another perfect square, and we got 2 rational answers, 2 fractions in this case. And then we saw some, starting on the next page, where we had discriminant was 52, which was a number greater than 0, but not a perfect square. And we got 2 irrational answers where the square root was still involved. Our next type of discriminant is if d were to be equal to 0. And if d is equal to 0, excuse me, 0 is over here, then we get one root, and the root we get is rational. We had one example that was the case. I believe it was number 3, so let's go back and look at it. If it chooses to load here, perhaps. Trying to see if it'll load if I do something. Not seeming to have an impact. There we go. The discriminant was 0. And the reason we had one solution here was because we're not adding or subtracting anything when we add or subtract 0. And so we just got one solution, and it was rational, either a fraction or an integer, which integer is technically a fraction. And then our other type of discriminant is that if d is less than 0, if d is negative. In that the case, we get two roots that are imaginary. And so if we look at some of these, that'd be like the last two we just did, where our discriminant was negative 20. So we got imaginary answers. And here our discriminant was negative 64, and we got two imaginary answers again. So on examples 1 through 4 on this page, we're just supposed to find the value of the discriminant and then use that to tell us the number and type of roots. And so we're not going to do the x is equal to negative b, all that stuff. We're just going to do the b squared minus 4ac. Not even the square root, just the b squared minus 4ac. And so here, if we do b squared minus 4ac, it's going to be 12 squared minus 4 times 2 times negative 13, which is 144, plus 104, and we get 218. Sorry, I said 114 on my first one, I think at least, but it's supposed to be 144, and this one's supposed to be 248. And so this is greater than 0, so we're going to have two roots, but they're two irrational roots because 248 is not a perfect square. On number 2 here, you plug this into b squared minus 4ac. b squared is 16 squared minus 4 times negative 1 times negative 64. So that's 256 plus, so minus 256, which is 0. This tells us there's exactly one rational root. Number 3 here, we need to get it equal to 0 before we begin, and so we get negative 4x squared minus 10x plus 84 equals 0. So we end up plugging these in, and we end up getting negative of negative 10, which means negative 10 squared minus 4 times negative 4 times 84, which is 100 plus 1,344, which gets us 1,444. And we're like, okay, well, it's positive, so we have two roots, but are we going to have two rational or irrational? It's 1,444 a perfect square or not? Well, you can just try taking the square root of it to note that it is, in fact, the square root of 1,444 is 38. It's a perfect square. And so these are going to be rational roots. And that's not one I have memorized myself. Now we'll go on to number 4. And as we go on to number 4, we notice that b is missing, which means that b is 0. So as you do b squared minus 4ac, it's 0 squared minus 4 times 3 times 24, which creates 0 minus 288. And because it's negative, we have two imaginary roots. Now, we've learned a lot of methods for solving quadratics in this unit. We've learned 5, as a matter of fact. Graphing, factoring, square roots, completing the square, and quadratic formula. And so there's so many because sometimes certain ones can and can't be used, but other ones can be used all the time, and sometimes it's to your benefit to use one over another. And that's why there are so many. So there's graphing, and this one can be used sometimes. This can be used when the roots are non-imaginary, so either rational or irrational. However, this one is not usually very practical. And the reason why we say that it's not usually very practical is a lot of times either we don't have a graph, or maybe if there are fractions and it's kind of hard to tell then on the graph where the fractions are at exactly, where the points are at perfectly. It also doesn't work when they're irrational, because then there's going to be just a bunch of string of non-repeating and never-ending decimals. And so it ends up not being practical a lot of times, unless they are integers. And so when would be a good time to use this is if the roots are integers. And the thing is you won't really know if the roots are integers until you, well, graph it. Now this can be eased when you're using a graphing calculator of sorts. That can help ease that complication quite a bit because the graphing calculator can take care of it for you. Factoring. When factoring is useful is, well, sometimes it can be used, some of the times. And so more specifically, when are those times? It's when the roots are rational. And you can tell if roots are rational by doing the discriminant or by attempting to factor. And if you attempt to factor, and let's say it's a trinomial, once we said as it's quadratic, and you make the x and you just can't fill out the x, so you find nothing that works on the side, then we say that's not factorable, and we'd have to move on and try a different method. However, when they are factorable, when they are rational roots, the like square root ones, for example, then factoring is a perfectly good method. Square roots can also be used only sometimes. And this one can only be used when there is no b term. Remember, b term was the one with the x, so it's like there's no x term. Is another way to think about it. Completing the square can be used always, all the time. When should you most likely use this, though, or when would it be best for you to use it? If there's no a. Let's try that again. If a equals 1, when aka there's like no x squared coefficient. I think I did too many f's there. Silly me. Another signal that is good to use completing the square is if the b term is even. Remembering that the b term is the x term. And the reason we say that it's even is a good idea is, remember, we do b over 2, or half of b, and then square that result. And so the fact that we have to divide by 2 makes that the b being even makes the problem a lot easier, so you don't have to worry about a bunch of fractions there as you're squaring numbers. And last but not least, quadratic formula can be used always. And when would be best to use it? Quite literally any time. However, it does often ends up taking longer and kind of more work, at least in my opinion. And so it's kind of, the best to use it when the other methods are inefficient, when the other methods aren't really working. So on this page, we have 4 problems here, and we're going to solve each of these 4 problems by one of 4 methods, either factoring, square roots, completing the square, or the quadratic formula. Now, we mentioned that not every problem can be factored, and not every problem we can use square roots on. So we have to pick those 2 carefully, or any problem we can do completing the square, and any problem we can use quadratic formula. However, you're still going to want to be choosy about when you use completing the square, Once again, looking for when the b term is even, very specifically. So we're first tasked with finding the discriminant of each, though. That way we know the number and type of roots. And knowing the type of roots, whether they're rational or not, can let us know whether or not we can factor. So to find the discriminant of each of these, we do the b squared minus 4ac. In this case, it would be negative 9 squared minus 4 times 1 times 21. Negative 9 squared is 81 minus 84. And so the discriminant here is negative 3, telling us that there are two roots and they are imaginary. So since they're imaginary roots, they're non-rational. It'd be best for us to pick either completing the square or quadratic formula on this one. Completing the square might not be as ideal because this is an odd number, and you'd end up having negative 9 over 2 and squaring that, and you end up getting a bunch of fractions. Now, they would work. We've done those. But this one we'll probably want to do the quadratic formula for. So I'm just going to go ahead and earmark that and put A in quadratic formula and say, hey, we'll probably use equation A there because they are imaginary roots, they're non-rational, and we have the B term is odd. And maybe I need to change that later as we look at more of them, but I'm saying, hey, right now I'm kind of targeting quadratic formula for that, for those reasons. Equation B, I do the b squared minus 4ac, and I say, okay, well, b squared is 0 squared minus 4 times negative 2 times 144, which ends up being 8 times 144, or 1,152. And this is actually not a perfect square, so this is too irrational. And I notice here that I'm lacking a b term. And since I'm lacking a b term, I'm instantly drawn to the idea of doing square roots, noting that for square roots we have to be lacking a b term. The b has to be equal to 0. And that's really our only requirement for square roots. Otherwise we can do imaginary numbers, we can do irrational ones, we can do rational, any type, as long as the b doesn't exist. The b is 0. And since I look at equations C and D and I'm like, oh, those both have b terms, b is going to be my equation for square roots, once again knowing that it's lacking a b term. Equation C here, we look for the discriminant, and that's x equals negative 4b. Gosh, my goodness gracious, let me try this again. B squared minus 4ac. There we go. And so it's negative 22 squared minus 4 times 3 times 7. And negative 22 squared is 484 minus 84. And that ends up resulting in 400. So this gives us two answers that are both rational, because 400 is a perfect square. So given that I'm going to get two rational roots, I'm noticing, hey, factoring might be a good idea here, because I have to have two rational roots in order to factor. And I don't know if D is going to give that to me. So I'm going to go ahead and earmark this one for C, and maybe if we can end up doing factoring on D because they're rational roots, I might end up switching these, but we'll see. Okay, we have to figure out what kind of roots we'll have on D. So on D here, we do b squared minus 4ac, and we get 6 squared minus 4 times 1 times negative 15, which is 36 plus 60. And this ends up giving me 96. So this is positive, and I'll get two roots. However, these are irrational roots because 96 is not a perfect square. And so now knowing that I have irrational roots, that removes the idea of doing factoring. And because I have a b term, that means we can't square root. So I'm stuck with either completing the square or quadratic formula. And because I have a b that is even, as opposed to on equation A when I had a b that was odd, I'm going to want to try and use completing the square on this one, because I can use completing the square when the b is even a little more easily. And so now I have my I have my methods picked for each equation. And so I'm going to go through and start solving these. So the equation for letter C, let's write this down for factoring. 3x squared minus 22x plus 7 equals 0. So I look for a GCF here. There is none. I go ahead and make the x. I do a times c at the top, which is 21. I do b at the bottom, which is negative 22. I look for two numbers that multiply to positive 21 while adding to negative 22. Knowing two negatives will do the trick, because two negatives will multiply to a positive while adding to a bigger negative. And 21 and 1, or 1 and 21, do the trick. I cannot use the shortcut here, so I have to rewrite the first term, rewrite the last term here. And the reason I can't use the shortcut is because a is not 1. I split my middle into the sides of my x, my little puzzle there, and I get negative 21x minus 1x, matching the variable there. I now group the first two and the last two in parentheses. The first two, I have a GCF of 3x, which left is x minus 7. The last two, I have a GCF of negative 1, knowing my parenthesis needs to start out positive, and I have x minus 7. I now say these x minus 7s are the same, so that's one of my factors, whereas the other factor is 3x minus 1, what didn't go in the first parenthesis, or wasn't in the parentheses, what was out in front of each. And now I set each of these equations equal to 0 and solve. So I do x minus 7 equals 0, 3x minus 1 equals 0, and I solve this first one, and as I solve this first one, I get x equals 7. Oop, I don't know what happened there, but that's interesting. So I get x equals 7, and I add a 1 and divide by 3 in the other one, and I get 1/3. Moving on to square roots, we said that we were going to use equation B for this one. So equation B, if it loads for me, we'll see, is negative 2x squared plus 144 equals 0. Quick reminder that square roots, you have to get the squared term by itself and square root both sides. So I'm going to subtract 144 from both sides to get negative 2x squared equals negative 144. I'll then divide both sides by negative 2, and I get x squared to be 72. Square root both sides, and I get x to equal positive negative square root of 36 times square root of 2, noting that the square root of 36 is 6. So I get positive negative 6 square root of 2. Moving on to the completing the square, which we said we'd do equation D for. Equation D, maybe this page will load. Fingers crossed. There we go. Is x squared plus 6x minus 15 equals 0. So for completing the square, I have to move that negative 15 over to the other side to get x squared plus bx equals c. And so I'm going to do x squared plus 6x plus blank equals, I'd have to add 15 to both sides in order to accomplish this, and get 15 plus blank. To figure out what goes on the blank, we do half of b and square it. So 6 over 2 is 3. 3 squared is 9. And I factor the left side into x half of b quantity squared, x plus 3 squared. On the right hand side, we get 24. Square root both sides. And I get x plus 3 equals positive negative square root of 4 times square root of 6, or 2 square root of 6. Subtract by 3 on each side, and I end up getting x equals negative 3 plus or minus 2 square root 6. That's my two answers. And the last but not least on this page, quadratic formula. The one we chose to do quadratic formula was equation A, which is x squared minus 9x plus 21 equals 0. So I plug this into my formula, and I get x equal negative of negative 9 plus or minus the square root of negative 9 squared minus 4 times 1 times 21 all over 2 times 1. And so this is 9 plus or minus the square root of 81 minus 84 all over 2. So that's x equals 9 plus or minus the square root of 3 all over 2. Square root of negative 3 all over 2. And if you recall, that's actually the same thing we got for the discriminant on equation A up above, because remember, the discriminant is what's underneath the square root. So we could have just shortcutted down to here on what's underneath the square root, as you notice down to the green. Now, the square root of negative 3 is the square root of negative 1 times the square root of 3, which is I times the square root of 3. All over 2. And 2 does not reduce with either 9 nor I, let alone both. And so these are the two answers. Now we're going to do some word problems and apply these to real life scenario. And these are all called projectile motion problems because they're having to deal with things being launched, thrown, hit, things like that. And when things are launched, thrown, hit, in real life, they follow the arc of a parabola. And now sometimes this parabola they follow is very steep like this, or sometimes it's more narrow like this. And sometimes as we throw something, we just only see this portion of it because we're just kind of throwing it straight out and down. But it still does follow a parabola where the other part of it might just be non-seen in real life. They can be represented by quadratic equations. And we can use this to help us find different information about the path that the projectile took. So this is often used in sports analytics, especially like football, for example, and to find the maximum height of a throw or the velocity on a pass and different things like that. We were able to find via this kind of math. So the height h in feet of a golf ball t seconds after it was hit from the ground, t for time, h for height, can be modeled by the function as following. And then find, first of all, the time it will take the ball to reach its maximum height, as well as what the maximum height of the ball would be. So keep in mind that it's going to once again follow this basic arc. And if we're trying to find the maximum height and the time it'll be there, we're trying to find the vertex. And so we're really just doing the negative b over 2a. In this case, instead of x equals negative b over 2a, it's going to be t equals negative b over 2a because it's t instead of x, t for time. And so it's t equals negative b over 2a. And b is 200, so it's negative of 200 over 2 times negative 16. And this is negative 200 over negative 32, which reduces or becomes the decimal 6.25 seconds. And we do want labels on there specifically. So that's the time it'll take to reach the maximum height. Now to find the height, we plug this in. Just like when we find the y value of the vertex, we plug in the x value. So to find the height, we plug in the time. And so h of 6.25 would equal negative 16 times 6.25 squared plus 200 times 6.25. And this ends up equaling that the h of 6.25, or the height at 6.25 seconds, is 625 feet. And we answered part A and B. Number 2, a rock is thrown off a bridge 40 feet above a river at an initial velocity of 96 feet per second. The height h in feet of the rock t seconds after it was thrown can be modeled by the function as following. Find the height of the rock 4 seconds after it was thrown. So we're trying to find height when t is 4. So this is telling us that t equals 4. So all we have to do is plug in 4 for t. And so h of 4 is equal to negative 16 times 4 quantity squared plus 96 times 4 plus 40. 40 being the initial height there, just so you know. And as we evaluate this, we end up getting it to be 168 feet. So that means it was thrown from 40 feet above, and it's like a person was standing here, for example, on a bridge 40 feet up, threw it up, then back down. On number 3 here, a cannon launched a cannonball from a height of 4 feet with an upward velocity of 125 feet per second. The height h in feet, of the cannonball t seconds after it was launched can be modeled by the following function. Find A, the maximum height of the cannonball, and B, the time in seconds it will take for the cannonball to reach the ground. So this is asking us to find the y value of the vertex, or in this case the h value of the vertex. So in order to do that, we'll have to find the t, or x value of the vertex, and then plug it into the function. And this is asking us to find what time does it reach the ground when height is 0, because at 0 feet up or down it'll be reaching the ground. So let's start with part A. So part A here, T is equal to negative b over 2a, so negative 125 over 2 times negative 16. And this ends up being approximately, or ends up being the fraction 125 over 32 after we do a negative divided by negative. Or we can approximate this to about 3.91 seconds. Now we don't want to find the time necessarily as our answer, but we need the time in order to find our next part, which is the height at that time, the maximum height. And so we plug this in and we do h of, and you can either do the 125 over 32, or you can do the approximation of 3.91. I'll just go ahead and do the more exact one. That's what I tend to prefer for me personally. And the nice part is I get to let my calculator do the work anyway on this after I plug it in. And we find h of 125 over 32, or h of approximately 3.91 seconds, to be approximately, as we round here, I'm not going to worry about the fraction answer, just the decimal answer. I'm going to round to 2 decimal places, or to the hundredths place, which would be approximately 248.14 feet. If you were to put in 3.91 rather than 125 over 32, you'll get a slightly different number than mine, but that's okay. As long as you show your work and I can see, hey, what did we plug in? And I'll be able to tell the answer you got out, and I'll be okay with that, as long as this math was still good to get this number. And of course, the math to get this number was still good. So that's part A. Now part B, we're trying to find the time in seconds it'll take the cannonball to reach the ground. So that's when height is 0. So we're going to set 0 equal to negative 16t squared plus 125t plus 4. So remember, 0 replacing the height, so it replaces the entire side. We're not plugging 0 into the equation because we're not saying time is 0. And that 0 height will be when it's at the ground. And so we're going to plug this into, we can solve this via some different methods. Your best bets are either going to be the quadratic formula or the complete square, but because this is an odd b term, not an even b term, we'll have to divide it by 2 and that would get messy. I'm just going to opt for the quadratic formula here. So x equals negative of 125 plus or minus the square root of 125 squared minus 4 times negative 16 times 4 all over 2 times negative 16. And this would be negative 125 plus or minus the square root of 15,881 all over negative 32, which gives me approximately negative 0.032, as well as approximately 7.84. Now here's the thing. Time cannot be negative, so this does not exist. And the reason we got a negative answer here anyway is because, remember, this cannonball was launched 4 feet above the ground. And so, let's say, like, the cannonball's on the cannon's on the ground there, but it launches it at this point going up, and back down. And so 0 feet would be here as well as here, where the cannonball is in red. And because the cannonball never actually touched the ground on this back end, that's why you see a negative time there for when it would have touched the ground had we launched it from 0 feet with the same specs, with all the other same things being consistent as a velocity of 125 feet per second. And so that's why we end up getting that time, but time can't be negative, so we rule that out and say it's the positive, approximately 7.84 seconds. A dirt bike launches from a 9-foot tall ramp at an initial velocity of 30 feet per second. The height h in feet of the bike t seconds after it launched from the ramp can be modeled by the following function. After how many seconds will it take for the bike to reach the ground? So again, we're looking for the height to be 0. So I'm going to plug 0 in for that whole left side and say 0 equals negative 16t squared plus 30t plus 9. You might notice a theme there that the a is consistently being negative 16. That's going to happen really just every time on these projectile motion problems, and that has to do with the physics of how projectile motion and velocity problems just work in general. So I'm going to plug this into my quadratic formula here to solve these two. So I'm going to get two answers, and one of them will again be negative in this case because we're starting from 9 feet up in the air. And so once again, kind of follow this arc where the ramp's here, so this part's going to be non-existent in reality, but you can still see it on the graph for what it quote-unquote would have been. Now, quadratic formula would be x equals negative of 30 plus or minus the square root of 30 squared minus 4 times negative 16 times 9 all over 2 times negative 16. Now, as we continue through this problem, we end up getting negative 30 plus or minus the square root of 1,476 all over negative 32. This will approximate to negative 0.26, which we said we can rule out, and 2.14 seconds, which is our answer. Moving on to example 5. The height h in feet of a kangaroo t seconds after it jumps from the ground can be modeled by the following function. What is the maximum height of the kangaroo? So once again, we're trying to find the vertex, and specifically the y value of the vertex, or in this case, the h value of the vertex for height. So we have to find the t value of the vertex, or x value of the vertex, using the negative b over 2a, and then plug that into the function. So t equals negative of 28 over 2 times negative 16, which ends up being 7 over 8 after you reduce. And so then we plug this in, and h of 7 over 8 equals negative 16 times 7 over 8 quantity squared plus 28 times 7 over 8. This ends up telling us that h of 7 over 8 is equal to 12.25 feet. That'd be kind of crazy to see a kangaroo jump 12,000 feet. Still kind of crazy to think it can jump 12.25 feet. An arrow is shot from a bow from a height of 4 feet. That's good for us to know, from a height of 4 feet. I'm going to go ahead and clock that there. With an initial velocity of 150 feet per second. Using the formula as following, if v is the initial velocity and s is the initial height, we need to know initial velocity, that's good to know. Then write an equation to model the height of the arrow t seconds after a shot, then find the height of the arrow 7 seconds after it was shot. So we're going to fill out this function, and so v is going to be our 150 feet per second, because 150 is our velocity, where s is our initial height, or 4. And so this is going to be, for part A, it'll be h of t equals negative 16t squared plus 150t plus 4 for the initial height, and that's our initial function. Now we're trying to find the height 7 seconds after a shot, so we just plug in 7. So h of 7 is negative 16 times 7 squared plus 150 times 7 plus 4. And that tells us that h of 7, didn't want me to write there for some reason, is equal to 270 feet. Number 7 here, a diver jumps from a diving board. Dividing board, that is quite funny actually, that's a good typo. A diving board, 32 feet above the water with an initial velocity of 12 feet per second. The height h in feet of the diver t seconds after he jumped can be modeled by the following function. How many seconds will it take for the diver to reach the surface of the water? So we're going above the water is for our height, where we're starting at. And so that means we're looking for a height of 0 for the surface of the water. And so we want to plug in 0 to our left-hand side, or replace the left-hand side with 0, and solve for that. Similar to how we did on some earlier problems when we wanted to hit the ground. This time we're just wanting to hit the surface of the water. And so I'm going to plug this into my quadratic formula, and I'm going to get x equals negative of 12 plus or minus the square root of 12 quantity squared. I don't necessarily have to say quantity there, but regardless, minus 4 times negative 16 times 32 all over 2 times negative 16. And this is negative 12 plus or minus the square root of 2,192 all over negative 32. And that is approximately negative 1.09, which we can rule out for being a negative timestamp, and 1.84 seconds. On number 8, the height h in feet of a soccer ball t seconds after it is hit by a player with his head can be modeled by the following function. What is the domain and range of this function? So here we want to know the maximum and minimum x values as well as the maximum and minimum y values. And so in order to find this, we have to think logically for a moment as far as the minimums go. So the lowest x value, or t value in this case, would be the beginning of the time. And the beginning of time is 0 seconds, aka when the soccer player hits the ball. And so the domain is going to start with 0, but we need to figure out what the domain is going to end with. And similarly, the range is going to start with 0 because the lowest the ball can get is 0 feet off the ground, aka the ground. It can't go below the ground, however. And then in order to find the maximum height and distance, we need to be able to find the vertex, as well as plugging in 0 for the function and figuring out what we end up having the end of the time be. Because remember that this arc, maybe a visual will be a good idea here. It's going to follow this arc, and it's initially actually starting slightly above the ground where this person is heading the ball. I'll use a green for the soccer ball here. And so 0 is the beginning of time when this happens. This is timestamp 0. It just kind of whooshed me over there. That's timestamp 0 right there when they're heading the ball. And then we're going to have our ending time right over here and our maximum height here, as well as our minimum height here. So the range is going to be 0 feet to whatever the feet is up here, whereas the domain is going to be 0 seconds from here all the way to whatever time is at this point. And so we need to plug in 0 in order to find the ending timestamp when it hits the ground. And so we're going to plug in 0 for our function, or replace the left-hand side with 0, and get 0 equals negative 16t squared plus 20t plus 6.5. And that would end up being, as we put it in the quadratic formula, negative of 20 plus or minus the square root of 20 squared minus 4 times negative 16 times 6.5 all over 2 times negative 16, which is negative 20 plus or minus the square root of 816 over negative 32. And this is approximately negative 0.27, which we can rule out because negative time does not exist, and 1.25 seconds. So this tells us that the domain is 0 to 1.25 seconds, or 1.52 seconds. You could also express that as an inequality, where you say 0 is less than or equal to x, which is less than or equal to 1.52. So that's our domain. And now we must find the range. Knowing the beginning of the range is 0, but we have to find the y value of the vertex, the h value of the vertex. So in order to find the h value of the vertex, we have to find the t value of the vertex by doing negative b over 2a. And so that's going to be t equals negative of 20 over 2 times negative 16, which ends up simplifying to 5 over 8. And now if I do h of 5 over 8, that's negative 16 times 5 over 8 squared plus 20 times 5 over 8 plus 6.5. That gives us a maximum height of 12.75 feet, meaning the range is from 0 feet to 12.75 feet. And the other way to write the range could be 0 is less than or equal to y, which is less, or I should put h and I should put t on my range, whoopsie doopsie, is less than or equal to 12.75. And either way you express the range between those two options, and either way you express the domain between these two options, once I fix this to be a t there, is perfectly fine. Last but not least for our word problems, number 9. The height h in feet of a baseball t seconds after it is thrown can be modeled by the function h of t equals negative 16t squared plus 86t plus 5. If the ball is caught when it's 2 feet from the ground, so the height would be 2 feet, how long will it take the ball in the air? So we got to replace the left-hand side with 2. So we have 2 equals negative 16t squared plus 86t plus 5. And now it's solve for t. And so we have to get this equal to 0 in order to use a quadratic formula. So I'm going to subtract 2 from each side and get 0 equals negative 16t squared plus 86t plus 3 equals 0. I already put the equal 0. And so now I plug this in the quadratic formula, and I get x equals negative of 86 plus or minus the square root of 86 squared minus 4 times negative 16 times 3 all over 2 times negative 16. Negative 86 plus or minus the square root of 7,588 all over negative 32, which gives us approximately negative 0.03, which we can rule out for being negative time, and approximately 5.41 seconds, which is our answer. Now that we've done all those word problems, the very last part of our lesson today will be solving this one quadratic equation through different methods to showcase how each method differs while still being able to get the same results. So we'll first solve it by graphing, and remember to solve by graphing, we want to find the axis symmetry, the vertex, and make a table to make more points. So here I'm going to find the axis symmetry first. I'm going to zoom in a little bit more so I have more room to work. And remember, axis symmetry is x equals negative b over 2a. So this will be negative of 6 over 2 times 1. That's negative 6 over 2, or negative 3. So that's x equals negative 3. I will then plug this in, and I will get negative 3 squared plus 6 times negative 3 plus 5 equals 0. That's 9 minus 18 plus 5 equals 0. Which is negative 5. Oh, I don't know why I'm putting equals 0 here. That's kind of silly of me. This should be f of x, really, not equals 0 on this. The equals 0 would be more so when you know you're already finding the 0. In this case, we are setting an equation, so this would really be equal to like y, or f of x, for example, or f of negative 3. And I'll actually put the f of negative 3 on the left-hand side. That's how we typically put it. And so f of negative 3 equals negative 5. And so that means we plugged in negative 3, we got negative 5 out, so that would be our ordered pair for our vertex. And now as I make my table, I'm going to put negative 3 in the center. And I'm just going to go from negative 5 this time, rather than going from negative 6 down to negative 3. Just for sake of time, since we're going to be going through multiple methods for this one problem. And as I plug in these numbers, the number negative 5 gives me 0, negative 4 gets me negative 3, negative 3 comma negative 4, and then negative 3 and 0 again. So go ahead and graph these points. So I have negative 5 comma 0, as I mentioned, and then all these other points as well. And we end up getting the x-intercepts to be negative 5 as well as negative 1, which you could write as ordered pairs as well if you'd like, or two separate x equals negative 5 and x equals negative 1. Now let's solve this by factoring. So in factoring, we'll want to set this equal to 0. So we'll have x squared plus, oh, I put minus, plus 6x plus 5 equals 0. And to factor a trinomial, we make the x. There's no GCF, and it is in the right order. So we do a times c, which is 1 times 5, that's 5. On the bottom, we do b. We find two numbers that multiply at the top, add at the bottom. Positive 5, positive 1 do the trick, multiplying to 5, adding to 6. And we can do our shortcut because it's a 1x squared. So our shortcut is just x plus 5 and x plus 1 equals 0. And now we can set each of these factors equal to 0. So we have x plus 5 equals 0, and x plus 1 equals 0. Next, I will subtract 5 in each side of this first equation and get negative 5. I'll subtract 1 on each side of the other equation and get negative 1. So once again, we get the same answers we had up above, which is a good thing. If we got different answers, that'd be quite concerning. Next would be square rooting, and actually we really can't do the square root method here, because there's the b term, so can't be solved because there is a b term. We could also think of the b term as an x term, the term with the x. And this isn't like a formal statement like, oh, anytime you have this, you have to say this word for word. It's just kind of us stating that, hey, as much as we'd love to solve by square roots here, I personally like the method quite a bit. We just can't use it when there's a b term. So next, completing the square. For completing the square, we'll want to start off with our original equation, but then we'll have to move that plus 5. And so I'm going to subtract the plus 5 by the other side, on both sides really, and I'm going to put a plus blank. And now what goes on the blank is half of b squared. Half of 6 is 3. Square that and I get 9. There we go. And then I factor my left side into my variable, half of b, quantity squared. On the right side I get 4 as I combine like terms. I now square root both sides, and I get x plus 3 equals positive negative 2. And then I split this in order to make my two cases. X plus 3 equals 2. X plus 3 equals negative 2. And in each case I subtract 3. On the left I get negative 1. And on the right I get negative 5. Once again, the same exact answers we've been getting on the previous methods. And that's my nice quadratic formula. So once again, my quadratic is x squared plus 6x plus 5 equals 0. So I'm going to plug this in my quadratic formula, which is x equals negative of 6 plus or minus the square root of 6 squared minus 4 times 1 times 5 all over 2 times 1. And that's negative 6 plus or minus the square root of 36 minus 20 all over 2. And 36 minus 20 underneath the radical is the square root of 16, which is quite convenient because 16 is a perfect square. So that's x equals negative 6 plus or minus 4 all over 2, to which I say, okay, I need to split this. One of my equations is x equals negative 6 plus 4 over 2, which is really negative 2 over 2, and equals negative 1, which is one of the answers we've gotten. And while we know, yes, the other answer should be negative 5, we'll confirm by doing x equals negative 6 minus 4 over 2. And negative 6 minus 4 is negative 10. And that ends up simplifying to negative 5. And so this just showcases here that regardless of the method you use, as long as you can use the method, so we couldn't use square method for square roots here, but regardless of the method you use, you'll get the right answers you'll get the same answers as long as you do the right math. And that wraps up section 4.8, which wraps up unit 4 of Algebra 2.